This is going to be a course on dynamic graph algorithms, and it will consist of roughly around 20 lectures. And I am not going to assume any prerequisite except an exposure to basic graph algorithms that everyone should know from their undergrads. So, what is a dynamic graph algorithms problem? Let me motivate this by using this illustration. So, what is a graph algorithm? You can even actually think of any algorithm in this way. So, this is a black box that takes an input, some graph, and then it produces some output. So, the input is the graph G, and the output, depending on the problem, it can be anything. Say it can be shortest path information or connectivity information, minimum cut, and so on. Okay. So, shortest path, connectivity, min cut, and so on. Now, of course, we measure the efficiency of an algorithm by its running time. So, we want algorithms with small running times. Now, what if consider a problem, say shortest path, you are given a graph, you output the all pairs shortest path matrix, and now suppose I just change the input slightly. So, earlier the input was I and the output was O, and now I suppose just insert and delete an edge in the graph. So, the input becomes I plus delta I, and the output will also change slightly probably. The question is, if this is the case, then do you need to run the algorithm again from scratch on this slightly different input, or can you use some information that you already have? You already know the answer to the problem for any input that is very close to the current one. Can you somehow reuse that information to give faster update times? Okay. And this is the underlying theme of dynamic graph algorithms. So, it can be summarized as just this question: can we do better than recomputing from scratch? Okay. And this is the question that we will try to address in this course. And as you can see that this question can be asked in the context of any graph algorithms problem. There is nothing specific about shortest path or connectivity or min cut. You can ask this about matching, about vertex cover, any classical graph algorithms that you have studied in your undergrad algorithms course. Okay. So, what I will do is the course will be organized as follows. The first lecture I will just give a basic introduction, then the next 14 or 15 lectures I will present some important papers from this area. There is no textbook or even there is no textbook or survey that I am aware of for this course, and I will organize these lectures according to the techniques that are being used. So, instead of focusing on specific problems, I will focus on specific techniques that are used in this area and devote say a few lectures to each technique. And then the last few lectures, probably 3 or 4 of them, I will deal with lower bound techniques, both unconditional lower bounds that are given in the cell probe model and conditional lower bounds that are basically very fine tuned reductions based on certain hardness assumptions. Okay. So, let us start with some basic definitions, and I will illustrate these definitions using this example, say shortest path. Okay. So, suppose we want to study single source shortest path in undirected unweighted graphs. Okay. So, before going into the dynamic setting, let us just study the static setting for the time being. So, you can think of the static setting as a data structure problem. So, it will be design a data structure such that it performs the following operations. Preprocess takes as a graph like this, and then there are these queries. So, in the preprocessing step, you are also given a source node, say, and the query is the distance between the source and a specific node. So, return the distance from the source to a node V. Okay. Now, we all know the best possible answer to this question, right? What can you do? You can give a data structure that just for the preprocessing step, it runs a breadth first search algorithm, runs BFS, and what will be the time? The time will be order of m time, where m is the number of edges in the graph, and let us say n is the number of nodes in the graph. And then you can build the BFS tree, and after that you can answer each query in constant time. In a dynamic setting, you also have the preprocessing step and the query step as before. Just in addition, you have to deal with an update operation. So, the updates are insert an edge, or delete an edge. From the graph. And the question is, design a data structure that can preprocess a graph, support these update operations, and support this query operation. And you want to minimize the update time. This is the time taken for the update operations, that will be called the update time. And the time taken for the query operation, this will be called the query time. And this will be called the preprocessing time. Okay. So, one more notation definition. We say that is dynamic setting is incremental if it only supports insert operations. And we say that a dynamic setting is decremental if it only supports delete operations. Otherwise, we will say that this setting is fully dynamic. So, this means it supports both insert and delete. Okay. Now you can note that the only thing that will change as we go from shortest path to connectivity to min cut to matching, and you can add your favorite problem here, is this query operation. So, for connectivity, the query instead of this distance will become are two nodes u and v in the same component or not. So, you just change the query operation, otherwise the model remains the same. Okay. Okay. Now, today what we will do is, we will study a simple algorithm for this problem, single source shortest path in undirected and unweighted graphs in decremental setting only. Okay. But before going there, let us just make one other very general observation. So, let me just use this part. There is actually always in any problem a trade-off between update and query time. So, suppose we just consider this graph, this is the update time, the x axis, and say this is the query time. Now, for this problem, suppose you just want to minimize the query time. Suppose you just want constant query time. Okay. What can you do? Anyone? Yes, exactly. So, just recompute the BFS tree after each update. Okay. So, then the update time becomes, you will have a point here, something here. So, in this point, I mean the update time is, sorry, the coordinate of this point I am just writing it here. The update time will be theta of m, but the query time will just be constant. So, after each insert and delete, just recompute the BFS tree from scratch. On the other hand, suppose I tell you, you just want to minimize the update time, but you do not care about the query time. Then what can you do? After each update, you just modify the adjacency list data structure using which you are storing the graph, do not do anything. And then when a query comes, you just run BFS from scratch, just run the static algorithm from scratch. So, then you will get a point somewhere here, where the update time will just be constant, because all you are doing is inserting and deleting an edge from a list, whereas the query time will become theta of m, because to answer a query you are running a BFS. So, we will be interested in non-trivial trade-offs. So, there is always a trade-off between query and update time. We will be interested in some non-trivial trade-offs that minimize both update and query times. Okay. So, now let us just move on to the main topic of this lecture. We will present an algorithm for decremental BFS tree, which is equivalent to single source shortest path in order of n amortized update time. Okay. And this is the reference, this is called Even-Shiloach tree. This is also known as Even-Shiloach tree, and this is used as a basic primitive in many other papers on dynamic shortest paths. The paper is called Online Edge Deletion Problem by Even and Shiloach. They are the authors of this paper, and it appeared in JCM 81. Okay. So, first of all, note that we are saying that this will maintain a BFS tree. So, the query time will of course be constant, because you are maintaining that BFS tree and you can maintain the distance of each node from the source. But the amortized update time is order n, n being the number of nodes. So, we have improved the update time from m, m being the number of edges, to n, the number of nodes. What does amortized update time mean in this setting? It means on average. So, you start with a graph, since it is a decremental setting, edges will only get deleted. So, let m be the number of edges in original graph or in initial graph, whatever you say. And it just means that theta mn will be total update time for m edge deletions. So, on average you are spending n time per deletion. If it were not the case, we would have said that this is worst case update time. So, for every edge deletion you would have spent n time, but this is only an amortized bound. Okay. Now, I said that I will try to organize this series of lectures as per the techniques used. So, what is the technique used to get this update time? There is no formal name for this technique, but let me just try to give my own name to it, and I will just call it principle of monotonicity. It just means this: you are maintaining a data structure, and each time an edge gets deleted, you have to update something in this data structure. Now, you can associate some number with the data structure and say that this number is only going to go up or go down after each update. It is going to change in only in one direction. Okay. And then you say that initially the number was something, say phi, and in the end it can never be negative. So, the total update time then becomes phi, right, because after each update you are just decrementing this number by 1. And similarly, it can be in the other way round. I mean that you say that you start with some number that is 0, and after each update you are just whenever the data structure does some work, you can increment this number by 1, and you can bound the final value that this number can take. Okay. And this seems to be very intuitive, right? I mean it's, but you will see that this principle is applied in many different dynamic graph algorithms problem, and we will devote at least 3 or 4 lectures to this principle. So, now how to maintain this Even-Shiloach tree? You will just maintain a BFS tree. So, this is the source, these are their children, okay. Now, first of all I will assign a rank to each node. So, rank of V is basically its distance from the source, or yeah.
Doubt is that why have you written the total update time to the order of mn? Are you assuming that all the edges will be deleted and then only the amortized time is order of n?
Yes, exactly. That is a very good question. This amortized update time assumes that you are going to delete all the edges. Suppose, yeah, it will be a good good problem if you can design an algorithm that does not have this guarantee, that if you just delete t edges starting from a graph, the total update time becomes t times n.
So you probably mentioned this, but I think I missed it. So this principle of monotonicity, does this apply only to the case when we are incremental only and decremental only, or when we have both?
Okay, good question. The first impression would be that it is applicable only in the incremental or decremental setting, because you yes, that should be the case. So now in the next few lectures we will see that this can be applied in fully dynamic connectivity as well, but then that is much more involved and it's hiding somewhere hiding underneath a lot of stuff, but that is much more complicated. But for decremental setting it's usually much more simple. Okay. Okay. So this, to maintain this BFS tree, we will first assign a rank to each node. This is just the distance from the source, and as you can see that the rank will also denote the level of that node in this tree. Okay. So this guy has rank 0, its children has rank 1, and so on. Now you can, in a BFS tree you have a nice property that an edge that is a non-tree edge, that is not part of the tree, can either be between two nodes that are in the same level like this, or it can only be between two nodes whose levels differ by 1. It cannot be that this node, say u, is at level 1 and this node v is at level 3 and there is a non-tree edge between u and v, because then in this BFS tree v's level would have been 2. Okay. So this is the property that we will use. Okay. So the list of neighbors a node has, it can be partitioned into 3 lists. One which I will call the parents of v. So parents of v simply mean the nodes u whose rank are exactly 1 less than the rank of the current node. So for example, if this is u1 and this is u2, then let us say that the parents of v are these edges actually, u comma v, not the nodes. So then u1, u2, this edge will be part of parent of u1. Okay. Then similarly we can define children of v. So these are the edges such that whose other endpoints are one level below. Rank u is going to be rank v plus 1, and finally friends of v. These are the edges whose other endpoints are at the same level. So this edge u1, u2 will be part of parents of u1 and children of u2, right. On the other hand, this edge, say between u1 and u3, will be part of friends of u1 and friends of u3. Okay. So this is just going to be the data structure that we will maintain, and you can see that we actually do not need to maintain the tree edges. I mean, if we just maintain these ranks and these parents, children and friends, then from this we can just infer the distance of any node from the source, right. It will just be the rank. Okay. Any question? Now there are just two properties that we need to maintain. What are the properties? I am not going to list down the obvious properties that say the rank of S is 0, that is one property, I am not listing that. Okay, let us just list this. So, property 1, rank of the source is 0, and property 2 is every node, for every node V, there is at least one parent, right, because it is connected to some node at its previous level. So, basically it just says that parents V is non-empty for every node V that is not the source, except the source, every node has at least one parent. Yeah, because if the graph is not connected, then since it is a decremental setting, you can just easily pre-process it and throw away the components that do not contain S. Okay. And there is one other property, which is that if you look at each node V, its entire adjacency list is partitioned into these 3 lists. There cannot be any edge adjacent to V that is not part of these 3. Okay. So, property 3 is each node's neighboring edges are partitioned into, I am just writing it short, and PV stands for parents of V, children of V and friends of V. As long as these 3 properties are maintained, you know that you are maintaining a valid structure, and these ranks are actually going to give you the valid distances from the source. You can prove it by induction, but I will just leave it as an exercise. Okay. This just follows from the definition of shortest path trees, and we will just ensure that these 3 properties are maintained. Okay. Now, you may ask, these are the data structures and these are the invariants that the data structure is satisfying. How will you answer a query? When a query comes, you just return the rank of that node. Okay. Now, the first thing is, how does principle of monotonicity fit in? How are we going to use this principle to bound the total update time? For that, okay. For that, we need to define the rank of an edge. So, rank of an edge, we will define it as the sum of the ranks of its 2 endpoints. Okay. Now, what can be the, and let us say that the rank of the data structure is, if you just take sum over all the edges and sum over their ranks, that is what you get. This is the rank of the data structure. Now, what is this rank of the data structure? What is its value, the range of values that it can take? It is definitely non-negative. So, you know this. and it is at most there are m edges in the beginning, and each edge can have rank at most 2 times n. Okay. Yeah. So, in the note that in the beginning the rank can actually be very small, it need not be 0, but it can be just 2 times m, because maybe it is just a complete graph. So, each edge has rank 2. Okay. No, each edge has rank 1, sorry, I take it back. Actually, I should say this, because each edge has rank at least 1, right. So, initially the rank is at least m, and finally the rank can be at most 2 m n. Okay. So, the principle of monotonicity will say that each time the data structure is doing unit amount of work, the rank of some edge is increasing by at least 1. Then what is the total amount of work that the data structure can do? At most m n, right, at most this difference. So, each time the data structure does order 1 work, and hence this and this will together imply that okay. Any question? Can you use the mic, please? Sorry.
Factor 2 instead of order, why would it be that if maximum number of edge, if you add it for this array, the rank should be 1 at least n, right?
No, for an edge, if it is very far away from this, then each node can have rank order of n, right.
Basically, all the vertices, it's like a long path.
Yes. Just consider a long path of length n, n minus 1.
Yeah.
Let us look at the last edge.
Yeah.
So, what?
So it should be n, right? Why 2 n?
It's rank 2 plus rank B, right?
Oh, okay,
Rank
okay,
U
okay.
plus
Sorry,
rank
sorry,
B.
sorry, sorry. Yeah. Okay, yeah. So that was fine.
Yeah. Okay. So, this is how we will get the update time of m n, and finally, so now all we will do is run the obvious algorithm for updating the data structure after an edge insertion deletion, the obvious thing that will satisfy these 3 properties and maintain these 3 structures, and then we will show that that obvious algorithm satisfies this principle of monotonicity. Okay. So, let me just erase the other part as well. 1 second. Okay. So, how to handle the deletion of an edge? This is the operation, update operation. Let us say without loss of generality that rank of u is less than or equal to rank of v. So, the tree is here, here is U. Now, this edge is either of this form, so that U and V are friends of each other, or V lies at a level that is exactly 1 greater than the level of U. So, let us just consider this case first. So, case 1, what do we need to do? We just need to delete this edge U V from the friends list of U and V. Will anything else change? No, it still remains a valid tree, right? Fine. So, just delete this edge, and this data structure is now updated, and all the 3 properties are still satisfied. So, this case will only take constant update time in the worst case. The more interesting case is when V is here. Okay. So, I will just write down what we are doing in case 2 here. So, this is case 2. What do we need to do? First, we need to delete this edge from these data structures. And by that I mean delete U V from the parent list of V and the children list of U. Okay. Takes constant time. Now, do we need to worry about U? No, U's position is secure, right, because U was connected to somebody else at a lower level already. But we need to take care of V, because it might be that V had only one parent and now this edge is deleted, and then V's level will increase, V's rank will increase. It's increased, right? Okay. So, now if you see first of all that parents V is still non-empty, then we can just return, right. This is the easy case. It means that U has some, V has some other parent here, say U prime. Then the entire tree remains unchanged. The only case that is interesting is when V's parents are empty, parent list is empty. So, we are just going to consider that case. So, when V's parent list is empty, let me draw this picture here. Okay. This is V, and say V is in level I. V's parents are empty. So, V now just has some friends in the same level and maybe some children. Okay. What will you do? You know for sure that if V has some friends, then V can settle in level I plus 1. right? So, we will just consider these two cases separately, but they are basically just one case. So, first of all you increase the rank of V by 1, and then you check if friends of V is empty or not. This is the bad case, because if friends of V is empty, then V's level might drop even further. So, if friends of V is empty, then you just mark V as dirty. So, you just create a separate list of dirty nodes whose levels you need to take care of. So, V is now dirty, and update the data structures. Since V changes its level from I to I plus 1. Now, what do I mean by that? This operation will be implemented regardless of whether friends of V is empty or not. Okay. Now, what does this operation entail? It means that you will first visit every edge incident upon V and then accordingly change its status. Now, you can just think yourself what will happen when you are visiting an edge of this form, say V comma u prime, where u prime is a friend of V. What will be the change in status? This edge will become V's parent. Earlier this was V's friend, now this will become V's parent, and earlier this was u prime's friend, now this will become u prime's child. Okay. So, this is how you will update the children list of V. Okay. What will happen to these edges? They will become friends of each other. So, there is this edge V and u double prime. Earlier this edge was child of V and parent of u prime, u double prime. Now, this will become friends of both V and u double prime. Okay.
Children of V, right? U double prime?
Yes.
So,
currently in this picture, V u double prime is children of V, is in children of V, right. So, now as V increases its rank, what will this become? This will become friend of V, right.
but its rank may increase as well.
No, but you do not know that. That is why we have marked it as dirty. That is why we have marked it as dirty, because we do not know if its rank will increase further or not. But tentatively V is now at I plus 1, and this guy will now become, instead of child of V, it will now become friend of V, and similarly instead of parent of u double prime, it will become friend of u double prime. Okay. Now, I can just write the pseudocode here, but it is not going to add any new insight. What I am just saying is, just visit every edge incident upon V and update their status according to this classification of parent, children and friend, and you can just work out yourself what it will be. The only thing that you now need to worry about is this: V drops one level, right? What will be the status of u double prime? U double prime had V as a parent. Now, that edge has become its friend. Now, its parent set might be empty, right? So, you need to check that, and that is why we are saying, as part of this step, while considering an edge V u prime with rank u double prime is equal to rank V plus 1. If after this update step you see that parents of u prime is empty, then mark u double prime as dirty as well. Okay. Why? Because u double prime had only V as a parent, now V has increased its level and u double prime's level also needs to drop. Okay. So, by the time you are done processing V in this iteration, this is just one whole iteration. By the time you are done processing V in this iteration, what we will find is there is no dirty node in level I or above, but in level I plus 1 there are a bunch of dirty nodes. Potentially V is dirty and all its children who only had V as a parent, they are also dirty. So, now you need to deal with dirty nodes in level I plus 1. Okay. And how will you deal with the dirty nodes in level I plus 1? You will just consider them in sequence and deal with them exactly in this fashion. So, the picture will look like this. Let me erase this part. If you want to visualize this as a figure, it looks like this. S, after the deletion of this edge u v, V was in level I and this is level I plus 1. In the more interesting case where u v was V's only parent, V has dropped to level I plus 1 and now it has resulted in a bunch of dirty nodes. All these dirty nodes are in level I plus 1. Now, V might or might not be part of this list. Okay. This is what has happened, right? When, sorry? Not necessarily, because if it depends on how you are implementing the procedure. What we said was that if we observe that V had a friend here, then we will not make V part of this list, because we know that V settles at I plus 1. Okay. But it depends on the, you can just say that you put V here, but then when you consider V, you observe that its parent is non-empty and then you make it non-dirty, equivalent. Yes, sorry, good point. So, now this is the new rank of V. Okay. Okay. Now, so what I just want to suggest is that this pseudocode itself is not important. What is important is you just want to maintain this classification of edges and you want to maintain these 3 properties, especially property 3, no, property P2, that is the one that you want to maintain. And each time you are seeing that there is a node whose parent list is empty, you are just marking it as dirty. This is what is going on. Okay. So, now you just have a bunch of dirty nodes at level I plus 1 and what will you do? You will just process them one after the other. What will happen? It will create some more dirty nodes in level I plus 2. But the crucial thing is you will first process all the dirty nodes in level I plus 1 before going to I plus 2. So, as if you are just cleaning the levels one after the other. So, when you take up a node say W from here, this guy is dirty. What does it mean? It means that it does not have any parent. So, it can have some friends here. It does not matter whether the friends are dirty or not. It can have some friends here and it can have some children here. and now W drops, what happens? Of course, you adjust the status of these edges, which list will they belong to, and then what will happen? Potentially W's children will become dirty. So, this creates some dirty nodes in level I plus 1. But the important thing is that you do not handle these nodes now. You first finish up this list and then you go to I plus 2. Okay. And now as you can see that the rank of a node is always increasing, right, which makes sense because the edges are getting deleted. So, the distance from the source will only increase. Okay. Now, the principle of monotonicity, it is not difficult to see, right, because the data structure is doing some work only when it is changing the status of some edge, right, and whenever it is changing the status of some edge, it's at least its one endpoint is increasing its rank. See, data structure is doing some work only when it is fixing a dirty node W, and when it is fixing a dirty node, the amount of work it is doing is proportional to the number of incident edges on it. And for each of these incident edges, their rank is increasing by at least 1, because W itself is increasing its level. Okay.
Could one node be dirty because of two different nodes at a higher level?
Yes, of course.
Right? So then in that case, that will incur cost for both those dirty.
Yes, but okay, let us draw the picture. You are saying that one node is dirty. Is this W here or this node you are talking about?
So I'm saying, say let's that lower level node, is it possible that it was proclaimed dirty because of two different nodes at the higher level? So this is I plus second.
Okay, I think it will not matter, but the way I define the algorithm, but I think it is just a matter of convention. It will not be the case, because when W is increasing its rank and you are probing this edge, say W prime, you are probing this edge, you have updated the status of this edge, this is now part of the friend list. You are just in constant time checking whether W prime has any other parent or not. If W prime already has one parent, you are not going to mark W prime as dirty. Yes, but what I think is that it does not matter. Even if you are proactively marking W prime as dirty, then what will happen is that sometimes you will find some node in the dirty list that is not dirty, meaning that when you just pick up that node, you see that this is not dirty, but then you are just duplicating that. You can just charge that work to what I am doing right now.
Exactly. So I was thinking you can get charged twice if you could have multiple proclamations of dirty.
Yes.
But which you said cannot happen.
Yes.
The only time you are calling it dirty is because you have exactly one parent.
Yes. Okay. So as you can see, you can go through the paper, you can go through this lecture again.
There you are letting each time restricted this order of 1 node, but I think I'm not seeing where when your this thing the age ranks are increasing, but the data structure is not doing order of 1 work, right? Because it will keep on doing till the so it's order of login work it is doing.
Order of login work, why? But think of it this way, when is the data structure doing some work? It is doing some work only when it is fixing a dirty node, right, or it is looking at a node whose one parent who lost one parent, and then the amount of work it is doing, it is only when it is dropping, it is increasing its rank in this sense, right. And then the amount of work it is doing is just proportional to the number of edges here. And now you might ask that, okay, these edges might drop even further, but that will be in the next iteration, and there also the ranks of these edges are also increasing each time. So, the data structure might do n work for this edge while fixing this particular edge deletion, but then the rank of that edge also increases by n, because each time the data structure is just touching an edge, you know that one endpoint is increasing its rank. Okay. So, here is the summary. All you need to remember is, instead of maintaining the BFS tree explicitly, just maintain this parents, children and friends list, and just ensure that each node that is not a source has at least one parent, and then you know that this is a valid representation of the single source shortest path distances. And now, when an edge deletion occurs in the graph, just update this data structure in the most obvious way that will come to your mind, in the brute force way. Just see what you need to do to maintain this structure, and then you observe that what you are doing actually has this very nice property, that each time you are doing some work, the rank of some edge is increasing by at least 1, and this can go up to at least at most order of mn, and hence the total update time is order of mn. Okay. Okay. So, this is for today's class.